I'm Brockton Sterling. I'm in a group with Benjamin Arledge Bottlinger, Ezekiel Malua Young, and Sean Odell. For our feedback project, we chose a self-driving car because in today's society there are a lot of accidents and deaths caused by reckless driving. And so to counter this, we're going to use a self-driving car. And with a big thing on the self-driving cars is cruise control. And the purpose of cruise control is used so that you can maintain a constant velocity. However, cruise control can be a harmful mechanism if the system has too big of a percent overshoot, or if the system cannot withstand disturbances, such as gravity and wind disturbances. Our goal is to design a system that can counteract disturbances while having a relatively low percent overshoot. This low percent overshoot will play a large factor in keeping this mechanism safe. As you can see here, we have our block diagram, with M representing our Prius and B representing our damping coefficient, which is wind resistance. And from our block diagram, we can get our impedance diagram, in which the values are mass equals 1,397 kilograms, and our damping coefficient equals 84, due to the Prius's low streamline.
So ultimately, this is the transfer function we came up with. It's a second order system with poles at 0 and negative 1,397 over 84. Since both these poles lie in the left-hand plane, they're going to be stable. And up next is Malua with further analysis.
So plotting our open loop system in MATLAB gives us this root locus plot right here. As you can see, both of the poles are located on the left-hand plane, which confirms our earlier assumption that our plant is stable. Answering more analysis questions, yes, we do believe that our system will be disturbed. This is simply due to the nature of roads and that our car may encounter rising or decreasing slopes. In this instance, we are fighting against wind resistance. As for our input, it has to be a unit step due to the characteristics of cruise control in that the person sets the desired speed and then goes to that. Okay, so for our final design, we decided to go with the PID controller. Here is our PID controller integrated with our transfer function, given right here. As for the three criteria that we wanted to meet, we wanted a rise time of less than 10 seconds. We felt like this was reasonable since the 0 to 60 time is approximately 10 seconds. So going from 10% to 90% of our desired speed within 10 seconds seemed reasonable. Our second criteria is that our percent overshoot is around 1 mile an hour. This translates into around 1.54% overshoot. And lastly, we want a steady state error of 0 so that our car, once a set speed, will follow that speed. Going to our rise time, plugging it into equations given from class, we get a natural frequency response or natural crossover of 0.22 radians per second. For our percent overshoot, we plug it into this equation and it gives us a desired phase margin of around 79.9 degrees.
Alright, so after implementing our PID controller with our transfer function and plotting the step response, we obtained our final results, which you can see here. We obtained a rise time of 9.5626, which is under our 10-second limit. And our settling time was at 15 seconds, which is also under a limit we had of 20 seconds for the settling time. And then finally, our percent overshoot, we calculated to be 1.2262%, which is under the 1.54% limit that we set for 1 mile per hour. After first plotting our results using the CISO tool, we got a phase margin of about 90 degrees, which was over our desired phase margin of about 79.9. So after some adjustments to our PID controller, we were able to get that phase margin down to about 78.9, which is just right on where we want it to be. And you can see we've got an infinite gain margin, so we're a stable loop, and that was at a frequency of about 0.22 bit.
Alright, so using our specs, we found our gain margin was infinity, while our phase margin, after converted to radians, was 1.377, and that was at a frequency of 0.228 radians per second. And also we found that our max time delay was 6.039 seconds. And with all this, we found that our Nyquist diagram showed that our system was stable because it does not encircle the point at -1, and also the loop has no poles in the right-hand plane. This is our system.